Today we start here. Today's lab is about the density, and the density is defined as you remember, density is defined as, somebody will tell me, what's the density is all about? Density, correct, is mass over the volume. It's a ratio, correct? It's a ratio. So since we have three types of states of matter, so we'll have solids, liquids, and gases, and each of those phase or state of matter will have different units for the density. So, for example, if we have a liquid, which is mostly is used for liquids, the units is we use the unit is to be mass over the volume, will be gram over milliliter, correct? For the solids, we'll be using grams per centimeter cube, okay, or grams per cc. Cc means cubic centimeter. So now for the gases, for the gases we are using units of gram per liter. So we have going there gram per cc or gram per centimeter cube. That's solids. Then we have gram per milliliter. This is liquids. And we have gram per liter. This is gases. This is the first thing we have to know about density. As I said, density is a ratio between mass over the volume. And since we have three different states, we can expect the units will be each time different, what we are using. So next, we have to look at the fact that the density is so sensitive to two conditions, temperature and pressure. So density is very sensitive to temperature and pressure. What it means that changing the pressure will change the density accordingly, because the mass will not change, mass over the volume. The volume change with the pressure, correct? As you will see later on in the Boyle's law, that's indirect proportional to each other, volume to pressure. And then the temperature will change because the temperature has an effect on the volume. So if the temperature and pressure changing, the density will change, correct? So the density values are very sensitive to temperature and pressure. So, but most of the time it's very hard to change the pressure. So we assume it's 1 atmospheric pressure is all the time is used, but then the temperature is always changing. We change the temperature, then the density will change. So the density will change. Okay, guys? This is just the first information about the density, mass over the volume. Then the dependence of the density on the temperature and the pressure, most of the time on the temperature, because the pressure all the time kept at 1 atm, 1 atmospheric pressure at sea level. So therefore the temperature is very, very sensitive. And you will see most of the time in the literature, they will give you the value of a density connected to temperature. For example, density D of H2O at say 25 degrees, for example, is, or at 4 degrees, is say 1.00 gram per ml. So this is for H2O. So you have to specify whether a subscript or just write it there by itself as to be density is 25 degrees or whatever, 22, whatever the temperature you are measuring the density in, correct? So this is the second item we have to see. The third item we have to look today, and this is part of the experiment, part one. So part one of the experiment is about, let me switch color here. Part one of the experiment today, you have to prove to yourself and to me that the density is an intensive or extensive. You have to choose and select whether is density is extensive or intensive. So we have the intensive versus extensive. So what's the difference between intensive and extensive? If I say intensive, what do I mean by intensive? It means that the value of the matter itself of the system or the physical property, which is density, does not change with changing amount. So density, and that's what really says, density does not change with changing amount. It means the density of one drop of H2O will equal the density of, let me take this one, will equal to the density of 200.5 liter of H2O, or 205.05 megaliter, million, so megaliter of H2O. So it does not really matter whether is the density is amount of it small, tiny, or huge amount. The density does not change. Correct. Only you can change the density if you change the two sensitive conditions, which is temperature and pressure. Correct. That's. But the amount itself is not changed. The amount is related to it being intensive or extensive. The density is an intensive property of the matter and does not change with the changing amount. That's period. Correct. Now, the extensive, on the other hand, extensive properties, property here, such as mass, volume, length of the matter. Those are extensive, means they are changing amount. The amount is changing. So extensive properties such as mass, volume, length of the matter are changing with changing with changing amount. Correct. On the other hand, the all temperatures such as boiling, freezing, melting points are intensive. They don't change of properties, correct? They don't change. For the matter you are using, those melting point, freezing point, boiling point, condensating point, deposition point, sublimation point, those are not changing because they are intensive properties of a matter itself. So now we did 3 items. Let me just make a conclusion. A mass is a ratio between, density is a ratio between mass and volume. As you will see, most of our, in chemistry and physics, we are using ratios. All the time we're using what ratios? The ratio, density is a ratio between mass and volume, correct? And it's sensitive to temperature and pressure conditions. That's number 2. Number 3, density is an intensive property of a matter because it does not change its value changing amount. Whether you use small amount or big amount of the matter, the density will remain for that type of a matter the same. It's not. So those are the 3 items we have to look into them before we go further to the experiment itself. Any other question you have? Tell me if you have any other question. Do you have any question? Do you have any question? Please. No question, I will go further. And then I'll switch here to the PDF file. And this will tell us the whole thing about the experiment. So this is the density here. And the same thing we did the whole thing here together. And today, the first part of the experiment, we'll do the test to see if the density is intensive or extensive property of the matter. The second part of the experiment will be determining the, as I show here, you can see it here. This is a graduated cylinder here, correct? And we'll be using the graduates. We'll determine the cylinder, metal cylinder, to determine its density, correct? By using 2 types of measurements. The first type of this measurement is called the displacement method. And I'll come and show you how to do that. And then using the graduate cylinder and the tabular and this metal to determine the density of this matter here. And then we'll come out in the second part and look what type of metal we have in this cylinder here. So you come here, and if you look at this here, you will do the experiment, and you have to come up with answer what type of metals you have represent this cylinder. What it is: zinc, it is aluminum, it is lead, it is copper, iron, magnesium, and so on. So this is what you will do the next. Then this is called displacement method. The other method is we will do it with the called dimension method. Dimension method, what you will do here, this cylinder here has dimensions. And if I look at this one here, this is the length of a cylinder, and this is the circle of the cylinder, the top. If you look at this horizontal, but I will be looking at this as vertical view. So this is the height, and this is the cylinder. So the volume of a cylinder is the area of the circle in the top multiplied by its height. The circle of this cylinder, the top of it, is by r squared. But I can't measure the r squared because the error will be large. So what I will do, I have to measure it from using the metric system, the milliliter, the millimeter or centimeter. From the edge to the edge, that's the diameter. Diameter is twice a radius. Divide diameter by 2, I get the radius. So then I'll be using the show you here. I'll be using the this is the formula I'll be using to determine the volume of a cylinder. Since I know the mass of this cylinder, I have to weigh it first. In both methods, whether displacement or dimension, I know the mass of it. I will divide it by the measure the dimension of the whole thing here, which is diameter divided by 2 give me the radius. I have to square the radius. Pi is 3.14, correct? So pi is 3.14. So then multiplied by the radius squared multiplied by the height, I get the volume. Mass over the volume, mass of the cylinder over the volume, I get the volume. I mean, I get the density mass over the volume. The volume is here. So those are two methods I'm using to get density of a solid. Density of a solid. Now, what does not say in the procedure, I want to know which method is the best. Is the displacement method is good, or the dimension method, and why? So that's we have to go. So let's do first. We'll go first to the first part, and let's do the first part here. And the first part is here. So what we have to do in the first part? Well, the first part here, I'm not going in details, but this is our graduate cylinder. As you see here, this is graduate cylinder. Use the plastic one. All the materials are in the back. See the other exit of the lab, the door, your left, at the corner, there's all the glassware and hardware will be found there for the experiment. So we'll take this one here. Everybody's following? So when we take this one here, we have to weigh it empty. We have to weigh with this one what? Empty. And doing this, let me see. So here it is. I'm weighing this one empty, which is, let me see here. This is the mass of the graduate cylinder empty in grams. Okay. Then I will fill it with 10 mL. Okay. You will fill it with 10 mL. So you'll fill it with 10 mL. So you'll fill it with 10 mL of H2O, Tabor. 10 mL. And remember, the graduate cylinder always give you what? The volume reading. It has to have 2 digits after the decimal. I'm not writing 10 mL like this. I'll write 10, 0, 0. I have to have 2 digits after the decimal. Or I did 9.9 and then 0. I have to have 2 digits after the decimal when I read my graduate cylinder. Okay, guys? So fill this one here with 10 mL. 10.00 if I get this one here, or you can estimate in between. Estimation always plus minus 5, but you can look at the estimation and try to put something in the background of this graduate cylinder to read very well. Sometimes it's very hard to read through it, but if you put something dark tissue in the back, you can read much better. And your eyes are always perpendicular to the bottom of the meniscus. You see the meniscus of the Tabor, you have to look at the bottom of it. You cannot keep it like this lower. You cannot take it higher. So it has to be really the meniscus. You are really 90 degrees. Your eye is 90 degrees at the bottom of the meniscus. So first you weigh it empty, correct? After weighing it empty, you fill it with 10 mL of H2O, correct? Then you go back and reweigh it again. Okay, reweigh it. By reweighing, I get filled with 10 mL, correct, guys? Everybody following? So 10 mL. Then the volume you put what we say 10 mL, 10.00 ml. That's the volume of H2O. So the mass of H2O will be B minus A. So B step, B minus A. B step minus A step. B minus A will give me the mass of the 10 mL I have inside. Is this following? So then the density will be, what's the density will be? I have 10 mL there, which is C, correct? So I have, this is D, correct? D is equal B minus A, and the density here will be will be, that's the mass, will be D divided by C. D divided by C, the mass over the volume, which is 10 mLs. Okay, guys, write it down here. So that's, I get the mass of the 10 mLs. That's the value here. Then you have to write the value here with the correct sig figs. And you have to have your reading of the volume of the gas cylinder has to have 2 digits after the decimal, because that's the uncertain values there, the 2 digits there you have. So then when you are done, you go for the second part. The second part, you have 10 mLs here, correct? And you have you have the mass of the cylinder empty. You add to the 10, 15 mLs. So we are comparing if our density of the 10 mLs will equal the 25 mLs. Why 25? Because you started with 10, you will add additional 15, 15 plus 10, the total is 25 mLs. So I'm taking this one out. Then I'm coming here to the second part of the first part of the experiment, the second part of the first. So I will be adding extra 15 mLs. Extra what? I'll be adding extra 15 mLs. Now the total will be how much? The total will be 15 plus 10 is 25, and put the 2 digits after the decimal. 2 digits here after the decimal. So this is total of milliliter, correct? Now I know when I added 15 mLs, I go and weigh. I weigh what? I weigh the whole graduate cylinder with the 25 mLs. So here it is, 25 mLs. That will give me the volume here, correct? The mass of it in grams. The mass in grams here, correct? So 10 mLs, I did that's the first part. Then I add 15 mLs, I go reweigh it. So the mass of the 25 mLs, that's filled. But I know from the first part, all the way the first part here somewhere, the first part, I know it's empty. How much is worth empty? Correct? That's the empty one. Empty graduated cylinder, correct? Empty graduate cylinder, I know the empty. So empty graduate cylinder and then filled graduate cylinder 25. This is filled. So E, step E here, correct? E minus A will give me what? Will give me the mass of the 25, which will give me A, B, C, D, E, F, will give me step F, correct? Step F at the bottom here. So, and then after that, let me just take this one out, then go further here. So then this is the new, that's not F. New volume is 25, sorry. This will give me the other one. So here it is, right? New volume is 25, 25.00, 2 digits I have, milliliter. When I subtract E minus A, will give me the mass, whatever the EF, maybe this is G here. G step, it will give me G, not F. That's F here, that's F, step F. Sorry about this. So this is G here. G is E, the top, E minus A will give me G. Now, calculate the experimental density. Density will be, correct? G, not gram, that's G. So density will be, the mass is, correct? E minus A divided by 25.00, correct? ml, which is E minus A divided by F step. So E minus A step. So everybody's following? We did first the 10 mLs. We did graduate cylinder empty, correct? Then fill it with 10 mLs. Go reweigh. Go weigh it. The difference will give you the mass of the 10 mLs. Mass of the 10 mLs divided by 10 mLs, the volume will give me the first mass. Then I added 15 extra ones, additional 15. That's total 25, correct? Then I go reweigh. The reweighing of the 25 filled the other cylinder minus empty one will give me the mass of the 25. Divided by the 25 total volume will give me the mass of the second part of the 25. So we are comparing the density of 10 mLs versus the density of 25. And we said at the beginning that the density is an intensive. So I'm expecting here, and let me just go here. I'm expecting here to those density will be identical, almost identical, correct? If they are not identical, then we have a problem. Then we have to they have to come identical. So question, compare the experimental densities of both. Explain how experimental results either support or refute the density of intensive physical properties. Well, you can't compare both of those, correct? So the 10 mLs, let me see here. You have density of 10 mLs and density of 25 mLs. They should be not identical, but very, very close to each other. So very close to each other. They have to come very close to each other. The density of the 5 mLs, the density of 25. They have to come close to each other. You come then, problem. Find the average. So you take the average of 1. This is density 1, density 2. Correct? So density 10 mLs plus density 25 mLs. And then you take all those here, divide by 2. That's you get the average. Correct, guys? You get what? The average. If they are close to each other, then you will say here, you come here and then make your conclusion here. That's if they are close to each other, then this is intensive. So then it's intensive. So that's intensive. If they are not close, then you have an error. They have to come up very close to each other, very, very close to each other. So then you take the average of the two densities of the 10 mLs and 25, add them up, divide them by 2, you get the average, correct? So you come here, after the average, you will calculate the percentage error. Percentage error is defined as theoretical value, which is, it's in the literature, which is the density of H2O is 1.00 gram per ml, 1, minus the average of the both readings, divided by the theoretical value, 1, equal, multiplied by 100, that will equal to percentage error. So here you can come here, and then you'll find percentage error. So percentage error here, that's the average here. That's the average density, 10 ml plus density 25 ml. You add them up, divide them by 2, you get the average density. Okay, the percentage error here, on the other hand, is you can come here and then calculate the percentage error. So what is the percentage error? Percentage error, guys, is you take the absolute value, so you don't worry about minus or negative. It's the theoretical value minus the experimental value divided by theoretical value. Take the absolute value here, absolute value both, multiply by 100%. Correct? The theoretical value, on the other hand, comes out to be, this is the theoretical value here is 1.00 gram per mil. And this is will be theoretical 1.00 gram per mil. Okay, guys? So then you do the whole thing. Now, suppose we'll come up with values just from our own, okay? So I will come up with my own values, just as an example, just to express an example here. So I said, well, my first density of the 10 mil is equal to 0.9870 gram per mil. The density of the 25 mil is 0.9790 gram per mil. So the average density. So how much? Somebody had calculated. Calculate for me that, please. Calculate that for me. So how much the average? So what's the average? Take them out, add, and then divide by 2. Divide by 2. How much is it? 0.9870 plus 0.9790. Add them up and you divide them by 2. How much is it? 0.97909. You have to be, so somebody has it. What's the value? No, just I need 4 digits because we have 4 significant figures, both. 4 sig fixed, 4 sig fixed. So what's the value here? Which one? Come on, guys. How much? 0.983. So 0.98. What? 0.9830, correct? 3. That's only 3. Then I will have to add 0 because this is 4 sig fix. Correct? You have 4 here. 4 sig fix. So sig fix here. And you have here the same thing, 4 sig fix. So your answer has to be 4 sig fix. So the percentage error, guys, now you calculate that for me. Tell me what. Don't forget to multiply by 100. So this is 1.00 minus 0.9830 divided by 1.00 and the whole thing multiplied by 100. How much is this? Okay. First, you use the sig fix regulation or rules for the subtraction in the top. You get 2 digits after the decimal, controlling the 4 versus digits of the decimal. So your answer in the top has to come up with 2 digits after this. That's the least digit. And then whatever sig fix coming from the top, divided by sig fix coming from the bottom. The bottom is 3 sig fix. And then you do the calculations and you multiply it by 100 and whatever the sig fix coming out. So how much is that? So how much is that? How much? What? 1.7? 1.7 what? 0%. Well, 1.70%, that's not bad. So it means your values has an error of about 2%. So an error about 2%, which is acceptable. So within the errors inside experimental errors. So that's acceptable. That's very good. Now, if I get higher percentage error, say 80, 60%, I have to repeat the experiment. So I cannot prove to myself that the density is intensive while the error is huge, correct? So they are not identical, not similar to each other, not even close to each other. It's 60%, but within 5 to 10% give and take the errors of the in the lab, that will be accepted. Okay, guys, everybody's following? Everybody's following? So take this one out. We take this one out, and then we'll come here, and then we'll find the density of a solid. Again, first of all, we'll do the dimension method. So the dimension method, how I do this? Well, I take this here, guys, graduate cylinder, and put my metal cylinder is here at outside, not inside yet. So I will fill this one here above the length of this cylinder. Why? Because I have to see some displacement of the tapper, correct? So maybe this one is reading. I will put it in 40.00 milliliters. Okay. So this is like this. Okay, filled with exactly 40.00 milliliters. Then tilted. It is, you can see it, I'm tilting this one here 45 degrees. Slowly here. How many milliliters inside? 40, correct? Slowly here. Then straighten up. Then read, maybe it went a couple milliliters up, say 43.5. So 43.5 came out up, displacing, correct? We're assuming there's no air bubbles there. So 43.5 milliliter, the displaced H2O up, minus the 40 I started with. That volume is the volume of this cylinder, okay? Are this following? Are this following? So with the displacement method, I determine the volume of this cylinder. So before that, I have to know the mass of this, because the mass of the cylinder here will be used in both in both dimension method as well as in the displacement method. So we started the displacement method, correct? So what we did here, we just filled this one here with whatever is above the height of a little bit higher of the cylinder height, as said here in my case 40 mils, correct? So then tilted, insert. I have to weight this one first. I have to know, because if you start weighting it without, you forget to weight, the mass of H2O weight will affect the volume, correct, and the mass of this. So it has to be a dry weight, and then you can insert the whole thing. See here, you insert the whole thing, and then straighten up. The difference here in the displaced H2O final readings minus initial reading will give me the volume of the cylinder. I have the mass, I have the volume, displaced H2O. That will give me the mass over the volume, will give me the density of the cylinder, correct? That's the first method. The second method here, which is here, guys, look at this. First, you come here and then describe all this stuff here. You describe the description of the solid. It's a cylinder, correct? Color is gray or shiny gray, and this is cylinder, correct? Okay, guys. Mass of the object, you have to mass it first. You have to weigh it first. You put whatever that the mass is in grams. Then you put in the graduate cylinder, correct? You don't weigh this one. You just put amount above the level above the height of the cylinder a little bit. So in this case, I'm here above 40 mils. So I can have 40 mils then. That's my initial reading, 40 mils. Tilt 45 degrees, slowly here. If you rush and then dump it very fast, you might get into problems with H2O being splashed out, and then you are losing your 40 mils, a couple of those milliliters for your 40 mils. So slowly here. See here, the feelings here. Then they will be displaced. Tapper will be displaced. That's my final reading after displacement. And I have then, I have original, initial, and final. That will give me the volume of the cylinder. Correct? So that's the That's the initial one. That's the final. That's the volume. I have here the mass. So the density of this object, will be, in this case here, will be density here. Somebody will tell me how this will work. What's the density will be what step? What step on what step? So we have the mass, correct? We have the mass B, step B divided by step what? By step C. C is final minus initial C. Step C. B over C. That's the two steps. That will give you the density of this material, correct? So you write it down. Now we have to do the second method, which is dimensional method. So here it is. The dimensional method, so you have to have the mass. The mass will remain as is here. The mass will remain as is. So you have the mass of this. Will not change. That's the mass of this. You don't have to wait next a second time. You can come and then measure the dimension of this. So the dimension will determine the height. So if this is the density here, correct? So from here to here, that's the height. And then from here to here, that's diameter, which is double the radius. Diameter is not the density. That D means for diameter. Okay, guys, that's for diameter. Everybody's following me here? That's for your diameter. So then you put the volume of a cylinder. This is the area. This is pi r square area. Area of the circle. So this is area here. You have to have the area, and then you multiply this one here by the height. Area multiplied by height give you the volume. And the mass of B. So after doing this here, so step B over D. So density here, density, step B over D. Step B over D, correct? So you have two now, two densities of the same material, correct? Now, you'll come here and look at the whole thing and say, well, let me see what material I'm dealing with. So I come here and see what material, okay? So I say, okay, I'm dealing with one of those here. Okay, so this one to me looks very light. Most probably this one here is aluminum, okay? The aluminum is here. Okay, guys? And then I will make an error, percentage error for both sides. See how those two methods will differ from each other. So here's the value. That's your theoretical value. Theoretical value. So the percentage error will be 2.70 gram per mil for aluminum here, for aluminum, for example, minus your experimental one for the displacement divided by 2.70. If that's aluminum, multiply by 100. Or the second one will be 100, 2.70 minus the experimental one. This is dimension. Absolute value divided by 2.70 and the whole thing multiplied by 100. Okay, guys. So you have two densities. You can calculate their percentage error. The theoretical value in this case, here to me, this is aluminum because it's so light. If it's zinc, it will be 7.14. That's bigger. Copper even worse, 8.92. Lead is 11.37. Can we have gold? Yes, but gold is very expensive, correct? You can't get one like this. That will be stolen. Correct? So gold is 13 even. Are you following me? 13. Even heavier than all of those values here, correct? Higher than all those values. So you will have those those are two errors of each method. The least one will be the best. The least one will be the best. So the least, let me just put this one here. Let me come here and then come here and then get into this. Calculate the percentage error measured closest to, yeah, so for the average, we'll not take the average here. Why we should not take the average here? Somebody will tell me. And that's, I think it's just an error inside the procedure. We'll not take the average. Don't take the average. Why? Why we don't take the average? Come on, guys, don't let me down. The first one I told you have to do what? Take the average. Why? And here I tell you no. That's maybe an error inside the procedure, but that's, we correct this error inside the procedure. Why we have taken an average in the beginning and here we are not allowed? I'm telling you, not allowed to do it. Why? Somebody will tell me here. Correct. There we use the same measurement, graduate cylinder and tab work. You added more tab work to the same tab work already to begin with, correct? The same method. Here you have two methods totally different, correct? So while the displacement method here, method here, what do you have? We have mass, correct? You weigh the cylinder, and then you have the volume. The volume is final minus initial, correct? And you have an error here in this, so you have the mass, this is error, and then the volume, there is error, minus error. So you have this type of error, which is linear error. So you can see that the error is in displacement method is linear. However, when it comes to the dimension, guess what? You have mass. That's another error in weighing, the same like the old one. However, you have by r square, correct, multiplied by the height. So this is an error in the height. There's an error inside the radius square. So you have here error what? Q. You cannot by all means comparing two methods to give you different error approach with each other. You cannot take the average of those. So when I measure the diameter here from the edge to the edge with the centimeter here, look at this, from the edge to the edge with the centimeter, that's an error here, correct? And this is r square, that's error square. Then the height's another error, that's square error multiplied by error, that's cube, error cube, that's a large error. So therefore I cannot make an average with the two different methods, two different errors, correct? So that's the reason I cannot make an error with those two different way of methods. So here, let me take this one here. So we said about this here, don't take the average. So this one here, just skip it. Okay, don't take average of those two densities. Okay, guys, but you have to tell me here in this, when you take it out, tell me what the best method. So the question is, what is the best method? Whether it's displacement or dimension. That's, yeah, don't take the average, but after you calculate the error, percentage error, you tell me what's the percentage error in both, and which one is the best one. And you can reason it why. Then you can see it's why. Then after you are done, you will do what? You will do your post-lab questions at the end of the conclusion. So the let me just go, and this is the post-lab questions here. You will do them. So here it is, the post-lab questions. All those four questions of post-lab questions, you can do them to calculate those densities. Now, if I look at the let me look if I can have the lab report for that. I might not have a lab report handy, but at least you get the lab report. Will have a lab report example. This is the first experiment, so don't worry about it. But you can go and look at the iCollege. We might be able to. I hope it will record this. So let me go to the iCollege, then see if we can look at one of the examples I posted for you in iCollege. So here it is. I'm logging in. Okay, I hope it will work. Okay, so far so good. I hope it's recording too. As I said, this is experimental stuff we are doing. So this is your lab. That's not your lab. Your lab is 303. Let's go back and look at your lab. So in your lab here, we have an example. So let's look at one of the examples, the PDF 2 here, for example. We have two examples of the PDF, and I think it's opening here. Okay, guys, this is the PDF. That's the introduction, correct? Then this is the procedure. Two procedures. Once we have intensive versus extensive, and then the second one is to test two methods, which one is good, dimensional or displacement. Okay, that's the two in your own words. You don't have to copy. That's your data. That's the tables. Those are the tables here, guys. Look at this. Those are the tables you collect. Those are the tables. This is table here for the second bar, and the other one here is the table for the second part. The first part. This is the first part, tables, and this is the second part, tables, correct? So then you will write the conclusion. Which one good method? The second part, dimensional or intensive, and why? And then the first part, you will say if it's your confirmation. You are confirming that density is intensive, not extensive. Then you come to conclusion, right? Then after the conclusion, you come up with the post-lab questions. After this, you come up with the post-lab questions. So if I go, hold on, let's see if I can. Okay, so, and then there is another example. I think if you look at the example here, there is another example here. Let me see. There is another example, density PDF, so you can look into that. So let me just look at if we can. This is another example of density. So, but this is the procedure. This is the density. That's another, not ours, but you get the idea. Those are the tables, then the conclusion and the discussion. So there you have two types of examples here, but use the one I showed you before. 5 components. Goals of the experiment, the density, procedure, 2 parts we have in the procedure, then data, the tables for each part, then the discussion, whether you get the intensive or extensive and why, and then which one method is better, whether it's dimensional or displacement. and then at the end you make your conclusion, whatever based on your findings, data, and then at the end you do your post lab questions after the conclusion. So with this, I will conclude the lab, and we'll do the extra the lab, and then we'll do the actual lab.